Okay, so now we're going to discuss the so-called common denominator method for dividing fractions. And this is a method that is probably not used too much in most elementary school curricula. However, it has the added benefit of, or it has the benefit, I should say, of being very, very easy to justify with pictures. If you compare this with our previous clip, very long clip, that illustrated multiplied by the reciprocal method of dividing fractions, this can be motivated in just a couple of minutes with a couple of pictures. However, computationally, it is going to add an additional step of needing to find a common denominator. Okay? So again, as a teacher, the more ways of methods of explanation you have at your disposal, the better off you're going to be. So let's just suppose, for the time being, that we were under the agreement that we needed common denominators to divide fractions. So let's just see how we would divide fractions if we did in fact have common denominators. So let's just take an example of 6/7 divided by 2/7. Okay? So if we thought about 6/7 divided by 2/7 from a measurement division perspective, then that would be interpreted as 6/7 is how many 2/7. And on a number line, we could think of that as 6/7 is how many jumps of 2/7. And we could easily represent that. Students are very familiar with number lines. They're very familiar with how to locate fractions on a number line. So we could draw a number line. We could illustrate, we could cut the interval from 0 to 1 into sevens. And we could quite easily see that the number of 2/7 that fit into 6/7 is 3. We would just take 3 jumps of 2/7 to get to 6/7 on a number line. So 3 is quite clearly the answer, but as we saw with our last clip, that's not really what we're after here. We want to teach students a general procedure for dividing fractions, so we're not so interested in the answer at this stage as we are in how did we obtain that answer, okay? So notice what I'm going to do now. I'm going to do a pretty sneaky teacher's trick here. I'm going to erase something that I already have, but it's the reason I'm going to do this is because I want to equate the problem 6/7 divided by 2/7 with another problem. So all I'm going to do here is I'm going to just erase all the denominators. Okay? And if I erase all of these denominators, then it is quite clear, and I don't change anything else about the problem. Now, the question that is being asked is how many 2's make 6? Right? And you can see that since the answer is not changing. The answer is still exactly as it was before. And the way we found the answer is exactly the way we found the answer before. Right? So what this illustrates is that actually the answer to 6/7 divided by 2/7 is exactly the same as the answer to 6 divided by 2. And this is a perfectly valid way of dividing fractions, right? Which we would maybe call a common denominator method, because if we have fractions that have common denominators, it is valid to divide them straight across the top. 6/7 divided by 2/7 is equal to 6 divided by 2. Now, you may be thinking, well, that this problem worked out really nicely because 6 is a multiple of 2. So let's see an example of how this would work when the numerator of the dividend is not an exact multiple of the numerator of the divisor. So let's take a look at 5/9 divided by 2/9. Again, from a measurement perspective, the question that's being asked is 5/9 is how many 2/9. Okay? We could illustrate this again on a number line. So we need to know the number of jumps of 2/9 that will get us to 5/9. And instead of illustrating this with literal jumps, I'm going to use little bar pieces to illustrate the number of 2/9 that fit into 5/9. And so this would represent kind of one jump of 2/9, if you will. So one jump of 2/9 is going to get us 2 2/9. Another jump of 2/9 is going to get us up to 4/9. And then the question now is, how much of a jump is needed to get from 4/9 to 5/9? Now, we're only traveling a distance of 1/9 to get from 4/9 to 5/9, right? But the question is, how many jumps of 2/9 are needed to get to 5/9? The answer then is 2.5, isn't it? One full jump is going to get us to 2/9. Another full jump is going to get us to 4/9. And a half of a jump of 2 ninths gets us all the way up to 5 ninths. Okay, so what we see is 2 1/2 jumps of 2 ninths get us to 5 ninths. Well, we know that from a measurement division perspective, the situation that is being reflected here is we're saying that 5 ninths divided by 2 ninths, the answer to this question is the number of jumps of 2 ninths that get us to 5 ninths. We've just seen that the solution is 2 1/2, which of course is an improper fraction, is 5/2. So even in a case where the numerator of the dividend is not an exact multiple of the numerator of the divisor, we still have the same process working. It's still a valid process. If we have two fractions with common denominators, then the way we divide them, or a valid way to divide them, is to divide straight across the top. 5 ninths divided by 2 ninths is the same as 5/2, and of course 5/2 is the same as 5 divided by 2. Okay. So again, there's pros and cons to either of the techniques for fraction division that we've learned. The pro of division of fractions with a common denominator is that it's very easy to motivate the correct technique. These pictures are very easy to understand because they correspond exactly to the same pictures we would have drawn with whole number division way back when. The drawback, of course, is that if we choose to divide fractions with a common denominator, then there's an extra step in computation, right? So we can compare the two techniques. So for example, if we wanted to divide 3/5 divided by, let's say, 2/7, if we simply learned the multiply by the reciprocal procedure, then we know that the procedure says, well, multiply by the reciprocal of the divisor. So we just take the reciprocal of the divisor and we multiply. And we have our answer very quickly. But remember, motivating the multiply by the reciprocal process took a long time. There were a lot of steps involved in that discussion, okay? So what you gain, once kids learn multiply by the reciprocal, the computation is very easy, but what you're kind of giving up is that it's kind of a hard process to justify. On the other hand, from the common denominator approach, we've seen that's an easy process to justify because the pictures are very clear. The problem, though, is we're adding an extra step of computation, right? Because if we are just going dividing fractions based on the fact that we can only divide fractions if the denominators are the same, we would need an initial first step of finding a common denominator. Now, that's not the worst thing in the world, because kids have already found common denominators in many instances in fraction addition and subtraction problems. So this is something they already know how to do. It's just a little more time consuming. So our common denominator in this case would be 35. We would have 21/35 divided by, in this case, 10/35. And once we have common denominators, now we have our rule that we just established, which says it is valid to divide straight across the top. 21/35 divided by 10/35 is 21 divided by 10, which is the fraction 21/10. So you see, of course, we get the same answer in both cases. So it's a question of, as a teacher, what you feel will be most beneficial to your students.